Okay guys, so let's finish up this chapter, the last one, which is applications, rates of change in circuit analysis. So again, let's recall or do some quick recap. Let's say we have a y function. Okay, so when we try to find the dy over dx, okay, the dy over dx or the y prime, yeah, we are actually we can use this information to find several things. It depending on the question, yeah. For example, the first one is you can find, okay, from the y prime or dy over dx, you actually can find the slope or gradient of the tangent to that function, to the y function. Okay. Second, using y prime, we can obtain the rates of change of a quantity. So this is what we are going to learn in a short while. We are looking for the rates of change of the quantity, in this case of the capacitor, involving the current of the capacitor and the voltage for the inductor. Okay. Third application of the differentiation is that we can find the increasing, decreasing or constant of functions. Okay, so if that function, let's say that function in the domain of a to b, alright, it is continuous, so it means that we can differentiate it. Then when we can differentiate it, we can find whether that function is actually increasing or decreasing or constant by applying the y prime or dy over dx. And finally, in my example here, we can use the y prime to find the value for the local minima or maxima of the graph. So for example, for the fourth application here, for example, if we have this graph of SpO2, okay, if you never heard, so SpO2 is actually the measurement of the oxygen saturation, okay, of your body. So for example, if you ever in your life admitted to the ward, okay, the nurse will regularly come to you and put a probe on your finger. So the probe will be clipped on your usually thumb, yeah, and from there it can measure your oxygen saturation value. So let's say if you get 60 to 100%, it means that your oxygen level in your body is all right. So if I can give a case, for example, in COVID-19 cases, okay, many of the patients, the decreasing, they are short of oxygen in their body. The SpO2 reading will show below than well, if your SpO2 is below than 80%, yeah, so your SpO2 reading is below than 80%, and if become worse, getting to 30%, okay, lower, it indicates a very serious problem to your body. It means that your brain will not get enough oxygen, and this will lead to hypoxia, which can lead to death. Right? So okay, back to this graph. So if we know the function of this graph, we can detect the y prime here to get the local maxima or the minimum here, the local minima. Okay, that's the application, the general application of the differentiation. Now let's go back to our main topic here. In this case, we will only focusing on the application of differentiation in terms of finding the rates of change in circuit analysis, since you are taking engineering, electronic or electrical engineering, so that is why we make it more specific. Okay, now for the capacitor, yeah, for the capacitor, this is the formula that you can that you need to apply, okay, to find the current for the capacitor. Okay, so actually this formula is already derived from you. So if you allow me to show you the basic step of this is, okay, you actually will learn about this later on during your EC2. Okay, if you are taking EC2 now, or if you are going to take EC2, so this is the things that you are going to learn later on, yeah. But anyway, I'll just give you a brief introduction so that you can get prepared for it. So you know that capacitor, it acts as to store the energy. All right, you have your power bank. Okay, you always use power bank. So power bank is actually a big capacitor. It stores energy. So by the time the power bank discharge the current to your handphone, the energy will be depleted and you need to recharge it again. So capacitor basically is consists of the two conducting plates. Okay, so one side is connected to the positive voltage source and the other side is connecting to negative source. So if this is the voltage source, when the positive one connected to the conducting plate here, it will give the positive charges. So for the negative voltage source connected to the other side of the plate, it will give the negative charges. So what happened here is that we will have negative charges over here. So the other side will get positive charges. Okay, so from this experiment, okay, the people previously found out that the Q is approximately, the Q is the charge, yeah, is approximately to the voltage. So when we want to do the equation, Q is equals to the C times V. So V is the voltage source, yeah. Well, from this we know that the C here is the capacitance value, and it is actually the gradient or the slope for this function. Okay, now how can we get this formula from this? Okay, so basically you need to differentiate it. Okay, so you differentiate the charge here dq with respect to time. Okay, so dq over dt. So this is constant, the C is constant. So what happened, we only differentiate the voltage, so dV over dt. And to your knowledge, dq over dt is actually I. So that is where this formula comes from. Okay, so this is the fundamental of it. Okay, you just need to remember, so I is actually the I is actually the instantaneous current through the capacitor. The C is the capacitance in farad, so this is the constant one, and the constant quantity, and the dV over dt is actually the instantaneous rate of voltage change, or volts per second. Well, don't get too panic about this. This is fun actually to learn, yeah. Just enjoy it, yeah. Okay, now we move to the second equation that you need to learn, the relationship between the voltage and the current for the inductor. So inductor behaves differently as the capacitor. Okay, that's the thing. Okay, not behave differently. What I mean is that both of them are we call them as storing energy elements. Okay, capacitor and inductors both are storing energy elements. What I mean by different works differently is that if the capacitor they require a voltage source to be connected to the conducting plate, but the inductor, the inductor is storing the energy through its magnetic field. That's the difference, yeah, through the magnetic field. But the common between them is both of them are the storing energy element. Okay, now back to this formula. So this formula, which is V equals to L di over dt. So this is actually from the experiment they found out that okay, maybe I can draw it to make it clearer to you. Wait, yeah, if I can change the color to something different than what we have here. Okay, so okay, you imagine, so this is an inductor. So we have a, so this is the winding. Okay, this is the typical form of the inductor. So we have the, this is the length, we have the cross-sectional area. Okay, this is the core material, yeah, the cylinder one is the core material, and we have the number of turns. We call it this, the winding element here. It is depending on the number of turns or n. Okay, now, so when people, previous people did the experiment, they found that if the current is allowed to pass through an inductor, they found that the voltage of the inductor, okay, so when they did the experiment, they found that the voltage of the inductor here is directly proportional to the time rate of change of the current, right, di over dt. So again, when we want to make the equation, so it becomes VL di over dt, where the L here is the inductance in henries, or you can say that this is the constant of proportionality. Okay, this is the constant of the proportionality. So that is all that you need to know, or you don't need to remember, because your test is going to be an open test, open book test. So you just need to know how to apply the formula, this formula, okay, according to the based on the differentiation techniques that you have learned previously. Now let's see some example. Okay, we only have one example here, which reflects the rates of change in electrical circuits. Oh, sorry, two examples. My bad. Okay, we have two examples here. So example 2.12. Okay, it says here, usually, well, it's a common that the question for this subtopic will be in a problem statement. Okay, so you need to extract the information. In the first place, you need to extract the information. So okay, the current through a 0.1 Henry. Okay, so 0.1 Henry is actually the constant, which is L, constant of proportionality. So 0.1 Henry. The current given is IT. Okay, IT equals to 10t times exponent negative 5t. So you are required to find, okay, the question is find the voltage across the inductor, okay, given that V equals to L di over dt. So this is pretty much simple. We know that V is actually L di over dt. So this is very simple, seriously, yeah. We just need to differentiate the I, okay, and plug in this value to here. Only that you need to be careful if this involve, this is Henry, but what about millihenry? So just be careful on the prefix of the unit, okay. So let's proceed with the solution here. So 0.1, so L di over dt, you need to differentiate this one, okay. So when you differentiate it, okay, you need to do step by step, okay. So 10t, you need to apply product rule, okay. Is one function equals to u, the v is e negative 5t. So you differentiate du over not du over dt, because I'm using product rule. So it's better I use this symbol. So this is 10, and v prime is negative 5 e negative 5t. Okay. Let me erase that so that we can make it smaller. Okay, so when you want to find it, apply product rule. So u v prime plus vu prime. Okay, so u is 10t, v prime is negative 5e, negative 5t, plus vu prime e negative 5t times u prime is 10. Okay, now when you times up 10 with 0.1, you should get what? You should get 1, right? So that is why when you times up, okay, when you times up this one with 0.1, what's left is that, okay, you will have, okay, this will become, this one will become t times negative 5e, negative 5t, okay, plus e negative 5t. Okay, so okay, we have this e negative 5t, the exponent here, so you can factorize it so that it will become, okay, negative 5t plus 1, or if you want your answer to be like the same like me, okay, we just need to rearrange the terms inside this bracket, so it will become 1 minus 5t volt. So usually you need to state the volt here, okay, the unit, the quantity for this function. Final answer here. Okay, alright, we finished with example 2.12. If you don't really get it how to solve this, okay, you just need to redo, and I'm sure you will understand how to solve this one. Okay, it's either you are weak on solving the differentiation when involving exponent, otherwise it is actually pretty straightforward. For example 2.13, okay, the question asks you to find, determine the current through the capacitor in this figure when t equals to 1 over 160 seconds. So again, this question gives you a hint to use this formula. That's why I told you, you don't have to remember this one. Usually we'll give you the formula, or if not, since it is open test, you can straight away open the module, okay, to refer to. Yep, so the solution, since this involve the VT, the VT involve sine function. Okay, it involves sine function, yeah. So that is why you probably see it's like a little bit difficult, but again, it's actually very simple. Okay, so we have this formula. Okay, I equals to c dv over dt. So first thing first, you solve the dv over dt part. I'm not going to teach you about this. So okay, the question is 120 sine 160 pi t. Okay, so this is actually very straightforward. Okay, you need to apply chain rule, okay, so that you can get the answer for this. Alright, wait now. Sorry. So this one you can get it by using chain rule. So you need to try this at home. Since you are at home already, so try to do this. Okay, and you just plug in the value here according to the formula, and this one don't forget, because the unit for the C is 2 microfarad. Okay, yeah, so it is 2 microfarad. Okay, 2 microfarad, there's a micro over there, so it is similar to 2 times 10 negative 6 power of negative 6. So you need to include this, yeah. Usually students forgot to bring together the prefix. Okay, if it is 2 milli, then you need to in your calculator times, okay, 10 power of minus 3 or 2 nano, so and so on. So you need to apply, bring together the prefix of that in your calculation. So that is why you can see, okay, here, and carefully times up, so you should be able to obtain this final current. Okay, this is IT. Make it short. So this is IT. Now the question asks you what is the value of the current when the time is 1/160 seconds. Easy, you just plug in this T into the T inside this bracket. We only have one T in the final solution here, which is 160 pi T. So make sure you plug in this value correctly, and finally you can get the answer. It's just that remember that this if I'm not mistaken, in your calculator it must be in radian. So if you put it in degree, I'm afraid that you will get different answer. So you can try it by yourself, yeah. Okay, and now this is exercise 2.7. This one is only the one exercise that you can try to do to see whether you can understand it or not. And for this exercise, the answer for it, you can refer to my previous video. Okay, my previous video, so to check your answer. So I guess that's it, until we meet again. Okay, and don't forget to do your revision from chapter 1 until chapter 2, because your question in test 1, no, you only have one test, sorry. Your test question will involve chapter 1 and chapter 2. Okay, before I end this, okay, I would like to share with you the question, the tutorial question. So I'm afraid that some of you are not yet ordering the book from the Shopee, or still waiting for the e-module. Alright, so I'm sorry for the e-module part. I'm not sure when you can get it, the link for it. But for the hard copy version, inshallah you will get it if you already placed the order. Some of the students already obtained it. This is week 4, right? So week 4, some students already obtained it. So for those who haven't received yet, please continue your tutorial questions based on this, yeah, the A, B, okay, and yeah, you can pause the video to see screenshot this part. Okay, this is the continuity from the previous page of the tutorial. Okay, let me check if we have, yeah, that's all. Or you can also scan the QR code as follows to get the exercise and tutorial answers. Make sure you don't use your Siswa email. Use your personal Gmail. Inshallah you can get passing through this QR code link, yeah. Okay, I think that's all until we meet again. Okay, so